Well, hello friends. Today we are going to do an exploit once again, because it's been a while, just a couple of days, and we're going to exploit symbolication. So let me show you what I mean. If we are, say that we're running some program, like right now we have Windows Server, right? And it's PID 12, so we can actually look at the current running stack of PID 12 and see that Windows Server is doing this stuff right now. And we hide the kernel addresses here so that you can't find out what's where in the kernel, but user space addresses are visible. And actually we get these, the kernel looks at the executable, in this case this Windows Server, and actually figures out what symbol maps to which address here in the stack trace. So today we're going to craft a custom ELF executable that instead of showing something here that's like a reasonable symbol name, we're instead gonna trick it into reading arbitrary kernel memory. Yeah, we'll start by just putting something in the kernel that we can fetch. So I'll just put something here like oh no, not static. Call it secret, and the secret will be hello friends. That's nice. Okay, and then I guess we can. Oh wait, hold on, I didn't do that right. There we go. So if we build everything this way, then we should have the secret address here. So we want to be able to read this address to get the secret. And I'm cheating a little bit here by, of course, looking in the kernel symbol table locally, but we're not going to do a complete exploit package today, but rather we're just going to create an arbitrary kernel read by symbolication. So let's see. We'll start by just making a new userland program for crafting this thing. I guess we can call it H4X, as in hacks, but with a 4. Pretty cool. Got to innovate the cool executable names here. So let's get some of the usual good stuff. So since last time, ELF executables, we actually validate them quite a bit more than we did in the past. So this is going to be a little trickier than it was before. And special shout out to Andrew, who worked a whole bunch on validation. But we didn't catch everything yet, and I'm going to show you something that we don't catch, hopefully. Okay, so let me just get started here. We'll create a buffer, and 16K ought to be enough for everybody, right? And we will also need libelf for the elf definitions. Okay, so header, it's going to be elf 32 e header 2 buffer. Okay. Oh wait, what am I doing? There's no star here. There we go. Okay, so header dot e machine 3 for 386. Anyways, let's just get to the point where we write it out so that we can start testing it. We'll just call it x. I'll create. If that fails, Okay, let's just get the basics up and going here, because this is going to take a little time to get everything right here, I think, but we'll have to get started somewhere. So no, I didn't do that right. Difficult password this time. All right, so hex. Wow, there are so many of those. And then we have the X executable, and we try to run it, and we get exec format error, which makes sense because there's a lot of things missing here, obviously. And we can see here that file has an invalid elf header. So I'm just going to be a little bit smart here and actually bring up the validation code that Andrew wrote. So we can go through it step by step here and make sure that it validates. So let's see, is elf header, or is elf? First thing we're going to do is we're just going to set the ident field like this. I guess this is the magic bytes. Every elf starts with the letters elf, I think. Is that what it is? Yeah. Oh, elf after a 7F. Okay. So 4 characters in total. Okay, and then this has to be... You can just copy these things. The class has to be elf class 32. I'm going to skip right past all your validation, Andrew. Because now we are wearing the black hat today. It is pretty funny to attack your own system instead of other systems, I have to say. Oh. Elf OS ABI System 5. And the ABI version has to be 0. And oh, there was a definition for that. Well, I'll just use that then. Okay, and then we have to have an E-type that's either exec, dynamic, or rel. I guess relocatable. But in our case, it's just going to be a straight up executable. Oh, geez, so many things. E-version is EV current, whatever that is, and then the header size. Size of elf32 e-header. Okay, and then here are some shenanigans detection. Let's see how far this gets us, what we already did here. So we're still complaining. File has an invalid elf header. All right. File has incorrect section header size. See, it's very helpful. It even tells us what's wrong. So we got to here. Okay. Section header entry size. Size of elf32 section header. And are we good? I didn't spell that right. Section header string table index is not a valid index given we have 0 section headers. Okay, well, I'm just going to go without the hoodie, but we are going to need some section headers, I guess. So section header count is, I don't know, start with 1. It should make it run the program afterwards. So let's see, failure loading. Entry pointer is invalid. See, now we're making progress. And actually, let me take this off because it is too warm in here too. LARP for too long as a hacker, but we can continue the programming part of it. So now the entry pointer is invalid. And that means that we have made it all the way to do exec. So we passed validation. Kernel thinks it's a valid executable, which, you know, it clearly isn't, so we need more validation, but we had to jump through a few hoops, so hoops are good. So we can't have a 0 entry, right? So what if we just say header.e entry, we enter at 2 fajillion. And actually, let me fix this up right away so that we'll just execl non x no whatever. And if that fails, we'll pair execl. Okay. So we are crashing. And let's see, we loaded the binary, and now we try to jump to this address, the entry address that I specified, because that's where it thinks the program starts, right? So far, so good. The kernel's behaving very correctly, just loading a program and trying to start it up, but it just doesn't work. So we're going to need to actually load some code here. And it doesn't have to be very complicated, it just needs to be something. So first thing is we'll need to create some program headers. So let's see, program header count, let's just make a single program header. And the offset will be, so last time I was doing this, I was using doing this pointer math and it was messing me up, so this time let's just make it a bit easier. Since we have a big buffer, we can just say like 1 kilobyte into it, we will do our program headers. And then we can say program header is a pointer to elf32p header, buffer, or even header e ph off. All right, cool. Then we can say program header 0 is a pt load, and it is line, I don't think we have to touch that actually, but we have to set some file size. We'll just load the whole file actually. And the file will be 16 kilobytes, size of buffer. And the memory size will be size of buffer. And the flags will be, wait, I forget what these are. Damn it, isn't it px or something like that? Okay, I don't remember. Elf exec elf. What are they called? Oh, pf. Wait, here they are. Pf. P flags. Readable and executable. That's cool. And let's see, the entry, we'll calculate him the very last now. So the entry will be this plus, I guess where we put the code, we can put it halfway into the buffer. And we'll make a code pointer. Actually, we can just do it this way. Something like that. And so let's write out some assembly here. Actually, or we don't need a dummy function. We can just do it this way, I think. Global hacks code. Is this how you do this? I don't remember. Hacks code, and then we do hacks code like this. And then we do something that will crash us. And then we say hacks code end. And then we can say extern c hacks code. I think we can pick it up this way. Hacks code end, something like that. And then, actually, we don't need these to be function pointers. I think they can just be. Can even do this. And we have memcopy code, hacks code. Hacks code, something like that, but we want to use the pointers for these guys, so like that. And we need memcopy. Exec format error. File does not have program headers directly after the elf header. Well. That's interesting. My convenience strategy did not work out. Okay. I thought that was going to work out. So it expected 52. See, that's another one of those nice little things that we put in there, because we try to make sketchy, skeevy binaries, and we should try to catch that. So let's see, expected at 52. Fine, just go be at 52 then, whatever. What's wrong now? Incorrect program header size. Wow. PH end size. Size of. More hoops to jump through. This is good. This is good with the hoops, because if I can. Okay, so now I have some assertion. The alignment is expected to be the page size. See, this should probably be a rejection of the binary rather than an assertion. So we'll make a note of that. Stupid elf related bugs. Fix me's. We should reject binaries with a bad pH alignment value rather than asserting later on. Okay, that's good. So we need to fix up program headers p-align to be page size. Okay, got a new crash. And could not instruction fetch at 2000, 2000. That's where we wanted to jump to, 2000, 2000. And the process regions are we're trying to jump there. Wait, we never actually loaded anything there. I have to set the program header to actually load there. 2000. I mean, 2 fajillion, actually. All right. So what do we have here? We jump there. We are there. We have mapped the elf at this exact address. And what's it 2000, I wonder? It was supposed to be our cool hacks code, but I feel like maybe it's not there. 2000 plus 8192. Let's see. I'm a little bit suspicious that this thing is not doing what I want it to do. So let me just see that I'm doing this right. Hex, name copy. Oops. Zero bytes. Well. Oh shit, I forgot to global it. Wait, do I have to do that? Isn't that how you do this? Dang it. Okay, I have to go and look at... Where's the trampoline code? I know we do this somewhere. We'll create the signal trampoline stuff. Wow, look at this. Why does it look so funny? Oh, it's Intel syntax. So we really just have these labels. We didn't need the global thing. And probably don't need that. But, oh wait, I'm stupid. Let's just do it the way that it was before. Okay. Okay, there we go. Okay, we're copying 3 bytes. That's good. And we got a GPF, a general protection fault, at this address. It's good. That's what we should be getting for a CLI instruction, because it's a privileged instruction that only the kernel can call to turn off interrupts. So now we've got things set up so that when we run the program, we run this. That's good. Now, what we want to do now is we want to trick the kernel into, in these crash dumps here, we see the symbolication. This is also accessible in the proc file system, right? So we want to make it so that this here, like when the kernel symbolicates this address, it turns up as the secret string that we embedded in the kernel, the thing that we're trying to steal from the kernel, right? So in order to do that, we have to make a symbol table for the executable. So that would be, how do we do this then? Header. We have to make a, oh shit, how does this work? how does it work? It's you make a symbol table section, and then a string table, and then you have to add a symbol and then link that symbol to the string table. So I think we'll just start by making a symbol table. Shnum. Did we already set up section headers? We have one, right, but we never actually made any. So let's just make a couple, like 3. And section header offset. Put this down here. That looks strange. Okay, so maybe here we can use the sneaky trick at least, please. 1 kilobyte into it. How big is one of these? Doesn't say. Well, whatever. 1 kilobyte's probably far enough into the file. So section header is elf32 section header, buffer header e section header offset. Okay, so now we can construct some section headers. So we'll make a section header type, make the symbol table, and the offset is going to be, I guess we'll put it at 2 kilobytes. And then the size of entries is going to be, there's a type for this, elf32 sim, right? And we are going to have 1 entry only, because we only need to symbolicate this 1 address. Okay, and we should probably make some more of these, because, or actually, let's make the symbol table next, and then we can add more sections in a moment. So we'll do sim is elf32 sim at buffer 2k. So this symbol table section now points at the 2 kilobyte mark, and at the 2 kilobyte mark we'll put some symbols. So this guy will be exactly this address that we are crashing at, and his name is going to be name number 0. Okay, and then we have to make a string table. So make a section with string table, and we will just put that at 3k, and the entry size, I guess it doesn't really matter. We can say that the size is like that. Okay, and let's see. So if we then put here at 3k, stir tab, is buffer this. We want this to be a char star, and then we can stir copy something here. Stir tab will make a sneaky. Okay, so if we can make this crash trace show sneaky for that frame, that would be really cool. It does not show sneaky for that frame. Okay. Why is that? I'm probably just missing something. Let's see. So why don't we go and look at the code that dumps out the symbols, symbolicate in elfloader. So what we do when we symbolicate, what we give the symbolication function is an address that we want to symbolicate, and then optionally an output variable where we put the offset into the symbolicated symbol. So like if you were like halfway into a function, then we give you back the name of the function and optionally also how many bytes into the function that you are. So that's what those are. And then what we do is that we, if we haven't already, then we fetch all of the symbols from the executable and then we sort them. And sorting them just allows us to scan for the right symbol. But this could be done in a more clever way. Like you could imagine doing a binary search or something. Right now we just do a linear scan. A lot of little things like that in this kernel that could be optimized with better data structures or algorithms, and we'll get to them eventually. But right now, let's just focus on this. So this is the, if we haven't already cached the sorted symbols, then this is where we cache them. And then if you symbolicate repeatedly, then we will have a cache of the symbols. So we allocate a region, and then we walk all of the ELF symbols in the image. And I guess here maybe we can print out something like symbol count. Symbol count, it's logical. And maybe here also we'll dump out each symbol as we encounter it. So value is symbol value, and name is, this is a string, but I don't want to try to print it right now because it will most likely be a bad pointer or null or something, and then we'll crash the kernel. So let's see, what did we get here? Wait, did I even build? I didn't build, okay. Let's set it up so that we build the kernel also. Okay. Here, symbol count, 0 symbols. Well, I guess that would explain why we're not seeing a symbol. So the image symbol count is the symbol table section entry count. So symbol count for section index. Just see what that is real quick. 0. Well, it is section 0, but are we doing that right? I wonder. Section 0, okay. And then the entry count is, if the entry size is 0, then the entry count is 0. But the entry size is this. But I wonder if we are in the right place here at all. With entry size, let's see what the entry size is. Mm-mm. 16. Wow. Okay. So then what determines this? Entry size. The entry count is the size of the section divided by the entry size. Oh. Okay. So we put size 1 because I figured it was 1 entry, but it's actually 1 times the size of. Great. Then we should be able to progress to the next roadblock, which will be, and now we have a symbol, and it has a value. Can't parse that out in my head, but I would assume that it's 2000, 2000, yes. And name is a null pointer. Okay, so we don't need that anymore. And symbol count is now 1, so that's good. Maybe we should print out the value in hex. And how do we get the symbol name to be the right thing? So we look at the elf image symbol name. We'll ask for a table string with stname. Okay. And we set stname to 0. So the table string gets the string table section index, which is computed in elf image parse when we look at the string tables. So the symbol table we find this way, and then the string table has some additional requirements. So it can't be it has to be a string table, but it can't be the section header string table, and it has to have this specific name in the section header string table. So I guess we need to make a section header string table. So that's like a second string table that gives you the names of each section. Forgot about that one. I guess we'll put that at 4. Okay. sh int. I don't think the entry size matters for these, at least not in our elf parsing. So size, say 1K. And here we'll make a section header string tab at 4K, and we will call it .stirTab. So, and then what was the setup for that? That the header section header string index has to be the index into this table, which is just 0. So section header string index 0. Okay. Wait, I feel like that did not do any better. Section header string index. Oh, wait. This has to be, it's not the index into the table, it's the index of the table in the section headers. So we'll put it up here, and his index will be 2. Oh shit, look at that. Okay, so now we have a name pointer. And the name is this, which is C00 bytes into this, which if we check with our Python friend, it's 3K into it. So it's the sneaky string right here. So we have a symbol in our symbol table, and it indeed points to the right place, but it doesn't show up as the symbol here. Why is that? That would maybe be in symbolication. So up here we just load the symbols, but now we've loaded them and we're good. And down here is where we actually scan the symbol list. So you loop through all of the symbols and check if the address is greater than address. If so, then we use that symbol. If the address is greater than address, why is it greater than? Why is it greater than? Oh, because I see. So we look for the first symbol after the address that we're looking for, and then we take one step back and take the previous one. I see. That's a little weird, but I don't want to change anything about how the kernel works, because that wouldn't be like proper. It wouldn't make this game. It feels like it would be unfair. So let's not edit the code here, but instead let's work within these rules. So then we have to have a second symbol, I guess, so that we can go past the first one. That's not so tricky. We'll just add a second symbol to the table here. So sim1, the value is 3 fajillion. And st name can just be the same as the first one. It doesn't matter, because we just want to hit the second symbol so that we can decide that, hey, the first one was good enough. It's a bit weird how we iterate over the sorted symbols when doing elf symbolication. It breaks if the match is if the very first symbol is a match. Okay. Okay, so then we just have to say that the table is bigger now. So that would be here. We now have dos. Frickin' 2 entries in the symbol table. Oh, why did that not work? Yeah, sometimes it doesn't boot and we have to make a new file system. I don't know why. Just little things. So, okay. Oh shit, look at that. All right. So now we got the sneaky right here. We are crashing at sneaky. So what can we do with this? Now we want to do some offset math here, so that we, instead of getting the sneaky string, we want to get our secret. So secret is at this address. So we will save that somewhere. Secret address. Okay. And then instead of the string table here at 3K, we want to put the sneaky address. No, not the sneaky address, secret address. And we need to offset it by this, which is the location where we always load elf executables, which we really need to change so that it's not always in the same frickin' place. It's silly that we always load elf executables at but since we still do that, I'm going to take advantage of it right now. And say that the offset is, I guess, this minus that. Wait, what am I trying to do? I'm not doing the right thing at all. Secret address minus. Aha! There it is. So we now have our secret in the stack trace. Now we just have to actually get it from the proc file system. So we can't just get it, like, because if the program crashes, then we can't just get it anymore because the proc entry disappears. But if we put it to sleep, then we can get it that way. So syscall, if we, let's see, let's do something simple like sc sleep. Wait, what is the number of sleep? That's what I wanted to know. 0. Oh, it's the very first syscall. Shit. Is it really? Okay. Syscall 0, sleep. Well, that's convenient. And the argument is a single unsigned 32-bit quantity. Very convenient. Okay, then we can just say mauve. What am I doing? Oh, well, let me write it this way. I don't have to micro-optimize the hex code here. So we'll just put this in the syscall number, and we're going to sleep for, let's say, 1 hour. Does that go in EDX, I think? And hex 82. I have to check if EDX is the second argument. Yes. Well, the first argument, technically, because EAX is the syscall number. Okay, so now if we run h4x, it should go to sleep. And then we should be able to find the X executable here at PID 18. And no, that was not the right one. Wait, what? Proc 18 stack. Oh, it is sleeping here. Wait. Why was I expecting this to work? Back up. This doesn't make any sense. I guess I thought it would. Or am I totally blind? Am I just totally blind? Right, we can't see where it entered from user space. Right, I thought maybe I missed it, but no, we can't do that. What if we just make an infinite loop? Like that. And then we will churn some CPU. Look at that. Maxing out at 100% just for a hack. And there it is. It's the secret string from our kernel. And we are fetching it by tricking the frickin' stack trace mechanism of all things. So basically, you could read anything with this, and it will. It will read until it hits a null byte. So until it reads a null terminator. But it's a pretty damn good primitive. I think it's a basically arbitrary memory read, almost arbitrary, because you can't really control the length. Cool. Well, so let's recap. I wonder if we can readelf in here. I don't have readelf. Okay, well let's extract this binary and look at it. On X. Wait, what? I can't stat? I cannot change ownership of X. Oh, of course, because I wasn't root. Okay, so now we have the binary that we've created. Let's examine it with readelf. Okay, so there is one program header starting at offset 52. Here's our silly little program. Here are the sections. Can we read the sections individually? Yes. We can see here, oh, this is where you see the exploit actually happening. So we made our symbol table and then two string tables. This one is the section header string table. And this one has a very, very sneaky offset that points at the secrets in the kernel. Man, that was pretty cumbersome to set this up. Maybe I should even... It's almost like I feel like writing this, turning this into like a library for producing ELF files. But at least I'll probably keep this around for next time if we mess around more with this, which we should. Anyways, let's fix this. So, because obviously, like, this channel is not just about hacking the system, it's also about fixing the system and defending against these things. So step 2, let's fix it and protect against it. So what are we gonna do? We have to validate some things here. So I guess just asking for the name of a symbol. We should probably check where we are getting the raw data. So before we return the raw data, we should say if is within image string is it's the string offset really. The data offset. Raw data offset, comma, size. We don't know the size. That's a bit tricksy. We don't know the size here. So what do we want to do? When we give you a string, we definitely don't want to read past the end. Table string. So should we check? I guess we can do a sternlen and then give you back a string object. That would be pretty neat. Where do we use this? Only here. This API is pretty not awesome, actually. And who calls this? Name. What if we made this return a string view instead? All right. And we'll make this guy return a string view. And this guy as well, because then we can bound them to the size of the ELF image. And you don't get anything outside of the ELF image. Okay, so table string. Table string, here we are. Okay, so string view. Oh, what's this guy about? Section index to string. That should probably be a string view as well. Okay. And let's go here. Wait, what? Oh. Okay. Now if raw data, oh wait, where do we start the image? If sh offset plus offset, let's compute this first. Okay. And if it overflows, we will return nothing. And we can even announce shenanigans. Computed offset overflow. Okay. And or it's good. Okay. And the max length is the computed offset size minus computed offset. Okay. Length is string len raw data sh offset plus offset. If computed offset is greater than or equal to n size, actually we can just do it this way. Side image. All right. I feel like I'm going to screw something up here and look silly, but who cares? We'll push forward, and I'm sure you'll tell me in the comments if I'm doing something stupid. And max length. So we'll use size t for these guys. And then we will say what we return is a string view of the raw data with the length. Like that. I think that's pretty good. Maybe we can turn this into a helper. Or do we need more of these, actually? To string. What was that awkwardly named one? Section index to string, right? Oh. So here we just want to do basically the same thing, except this is section header to string. I think we'll make a helper here. Table string and assign table index, and then we'll copy this and we'll use the table index. This can be const. Okay, and then here we just have to return table string for section header string, section index thingy dingy, comma offset. And here we use the M string table selection index loop. Okay, now we're gonna have to fix some places, I guess. Yeah, we can't stir comp anymore. That's okay. We can now use regular old operator equal. And where are we then? We are on line 137. Sorted symbol. So const char. Well, this will have to be a string view instead. But that'll be better. Demangled. Oh shit. Can't pass a string view to the demangler. I'm gonna have to pass. Oh, can we make it take? Oh, demangle is our API. Oopsie doopsie. That's my bad. Then we can totally make it take a string view. And does this thing by chance take a size parameter, please? Length. Wait, is that the buffer length or length of the buffer containing the demangled name? A null terminated character string. Oh, that's so annoying. Freaking C++ ABI, you require me to give you an alternated string? Ah, all right. That's very, very upsetting. I guess I will just have to do this then. Turn it into a string, which will null terminate it, but it's a completely useless heap allocation that we throw away immediately, just to get that null terminator. There's probably a different way we could do that, but it's very convenient. So I'll do it this way. And then if we ever discover that this is slowing things down, then we can go and do something about it. What are we forgetting here? Oh, we can't pass void star like that. Okay, we got some stuff in process at 4234. Address for kernel symbol. That's fine. For kernel symbol. Where was that even used? Relocation symbol name. Okay, fine. Stern comp. Wait, stern comp is not a thing in the kernel? It is right here. No matching call. Maybe it's not exported in the header. Stern comp. No, it's right here. Okay, what am I missing? Oh, I'm passing a string view. Stupid. Okay, 4234 still. Oh. This is a nice improvement regardless, I think. Because now we are fixing up a whole bunch of not checking for null terminators. Ah, stuff getting better. Isn't it nice? So, can we build 4281? Okay, then we have to do a bunch of these, but this will also be much nicer. Oopsie. Oh, we should probably sync actually. It appears to be calling shenanigans quite a lot. Does it still boot? Yes, it does. Okay, I think we may have gone a little too hard on the shenanigans there. So let's see, table string, computed offset, outside image. This doesn't make any sense. This comparison is stupid and stupid. Obviously, it's okay if it's smaller than the size. That's the whole point. This is the condition that we want to be checking. All right, let's hex it. So what can we see is cat proc 18 stack. Ooh, we got some frickin' null, and look at that. Calling shenanigans. Nice. Very, very nice. Cool. So let's get rid of some of our debug code here. These symbol hashtag stuff. Okay, so let's look at our changes. Blah, blah, blah. I think we don't need the secret anymore. Now it just straight up doesn't work anymore. Isn't that nice? And oh wow, that's pretty nice and tidy change. So what did we change? We just made symbols be string views, and then we made elf image hand out string views. And if you compute an offset that's outside of the elf image, then we will call shenanigans and give you a null string. And if it's within the image, then we will say that the max length is the size of the image, the distance between the computed offset and the size of the image. And then we measure the string from that point with a maximum of max length, and then give you a string view with that length. That's very, very good. And then the rest is just updating for the string view API change. I mean the elf image now using string view. So let's look at Windows servers usually 12, and this does not look very good. Why do we see all that? Oh, because I didn't rebuild. Okay. Wow, look at all those symbols. So many of them. Stack. Okay, we can see Windows Server just fine. And if we try to hex it, hex is 20, prop 20, stack, shenanigans. Cool. All right, so let's commit this. Let's see, maybe I'll put this into the tests directory as well. So here's one, h4x, kernel tests, no, wait, tests, kernel, f, symbolication, kernel read exploit. Boom. And we'll have it. Don't lose these things. So let's see, kernel plus libelf, really. Protect against don't blindly trust elf symbol offsets during symbolication. In symbolication. It was possible to craft a custom elf executable that, when symbolicated, would cause the kernel to read from arbitrary addresses from user-controlled addresses anywhere in memory. You could then fetch this memory via proc pid stack. We fix this by making elf image without string view rather than raw const for symbol names after validating. In case a symbol offset is outside the elf image, you get a string, null string view. Okay, the next test is this loop. All right, nice. All right, so I think that we are done for the day, so that's going to be it for the video. So I want to thank you for watching, for hanging out with me while I work out how to exploit this and then make a fix for it. I quite like this video format. It's just it's a little bit draining to make, but it's really fun, and I hope it's interesting. I really hope you saw something interesting here, and I hope that your projects are going well. And thanks everyone for visiting as usual. What did I want to say? I don't really want to say anything. Thanks for hanging out. I will see you next time. Bye.